differentiate cos x with respect to x from first principles. So first up, dy by dx is given by the limit as h tends to 0 of f of x plus h minus f of x all over h. Just a little bit of information where that comes from. We've got some sort of function. We pick a point here, x. This is our function, y equals f of x. So the value of the function here is f of x. Go slightly further along to x plus h. We can control h. It can be as small or as big as we want at the moment. The function is then going to be f of x plus h. Notice it's inside the function because it's being applied to x. And then we want to find the gradient between these 2 points. So it's rise over run. F of x plus h minus f of x is the rise. The run is then just h, and that is the gradient of this chord, essentially, between these 2 points. If we want the instantaneous gradient at the point x, then we just move this point closer and closer together, which is where the limit as h tends to 0 comes in. So just a little bit of background on this amazing formula. So for us, we've got y equals, hold on, let's say that, f of x is equal to cos x. But this is also going to be my y. So I'm going to be substituting it in. I've already got my f of x. Right, what we need to do is find out f of x plus h. This is going to become cos of x plus h. Then we can use our addition formula. It's in the formula book, but it's cos a plus b. It's cos a, cos b, minus sine a, sine b. So here we will get cos x, cos h. There is a function called cosh, by the way, cos hyperbolic, but I don't think we need to worry about that here. If you're doing further maths and you want to kind of be careful, then maybe a bracket around it. Minus sine x, sine h. I honestly wouldn't stress about the brackets though. Okay, and I think we're ready to substitute this in because not much else we can do with this at the moment. The only thing to think about is the fact that h is going to be very small, but I think at the moment it's not. It's only until we put it in the limit that we have to consider that. So dy by dx is going to be this limit as h approaches 0 of cos x cos h minus sine x sine h minus cos x all over h. Now I'm going to just rearrange this slightly. Let's keep it all in this limit, but I'm going to factorize the cos x out of the first and the third terms. I'll leave the second one be. So it will become cos x times cos h minus 1 all over h. And in fact, I can just divide that one by h. You can do that with fractions. You can put it over the whole thing, but you can also just divide one of them by it. A bit like if you had 8 times 2 over 4. You could do 16 over 4 to give 4, or you could just do 8 divided by 4 is 2, and then times by 2 after. Yeah, it's all about the order not mattering. And then this next one will become sine x times sine h over h. Put this in a big bracket because it's the whole limit. Okay, so we now need to consider what happens to cos and sine as h gets small. So I'm going to go into some detail here. I'm not sure, I don't think this is required actually, but I think it's good to show, so let's do it. So for small h, cos h is actually approximately, this is given the formula, but 1 minus h squared over 2. In fact, there's a cos h can be like have an infinite series, a bit like when we do a binomial expansion. I'm not going to go into detail on that here, but it's just all the rest are being truncated. Because we're dealing with small h and all the other terms are going to be small, that's often what we do with binomial. And in a similar way, sine h is actually approximately equal to h. So as h tends to 0, cos h actually tends to 1. And sine, do you know what? I need to be a bit careful here because it's going to be cos h minus 1. I need to not just consider cos h, I need to consider cos h minus 1 over h because h is also tending to 0 on the bottom. So cos h minus 1 over h is going to be approximately 1 minus h squared over 2 minus 1 over h. And I also need to include this limit as h tends to 0. The ones are going to cancel. I'm going to get the limit as h tends to 0 of minus h over 2, which is going to equal 0. You don't need to go into this level of detail, actually. You can literally just say as h tends to 0, cos h minus 1 over h tends to 0. I do mean that it tends to 0, by the way, rather than it equaling 0, but it's the same idea. And then in a similar way, sine h over h, which is in our second term, is therefore going to tend to h over h, which is 1. And that means up here, we're going to get cos x times, now remember we said it became 0, cos x times 0, that's just going to go, minus sine x times 1. And that is our derivative shown. So if y is equal to cos x from first principles, we have shown that dy by dx is equal to minus sine x. Quite technical, but it's something you can practice and learn. Sometimes the question gives you this information, but here I'm just erring on the side of safety and showing it in enough detail.